July 28, 1942. Elko Naval Division Boatyard, Bayonne, New Jersey. 9:47 p.m. The Navy inspector stopped counting at Regulation Violation 12, overwhelmed by the unauthorized modifications a civilian mechanic had made to a military patrol boat without clearance, without approval, and in direct violation of Bureau of Ships technical orders. Lieutenant Commander John Harley, assigned to Motor Torpedo Boat Squadron operations and responsible for ensuring all PT boats met Navy specifications before deployment, stood on the dock watching mechanics drain what appeared to be aviation fuel from tanks that were explicitly, categorically forbidden from carrying anything except standard Navy 80-octane gasoline. 50 feet away, floating in the oily water of Newark Bay, sat PT-59, a 77-foot plywood boat that had been modified with high-compression engine heads, enlarged carburetors, and fuel systems designed for 100-octane aviation gasoline that Navy regulations absolutely prohibited in small craft. What Harley didn't know was that he was witnessing the result of a 3-month underground engineering project that had violated every fuel safety regulation in the Navy manual, but had accidentally created the fastest combat vessel in the U.S. fleet, a boat that would reach speeds no patrol craft was supposed to achieve and establish tactics that would redefine naval special operations. The PT boat with the outlawed fuel. A vessel that Navy safety officers had condemned as a floating bomb waiting to explode. But between July 1942 and the end of the Pacific War, the modification that should have resulted in court-martials instead produced a generation of patrol boats that could outrun, outmaneuver, and outfight anything the Japanese Navy could deploy against them. And it started with one mechanic who understood that the rules keeping PT boats slow were the same rules getting PT boat crews killed. The story begins not with the modification, but with a fundamental design compromise that made early PT boats dangerously inadequate for their mission. December 1940, Electric Boat Company, Groton, Connecticut. The U.S. Navy, recognizing that war was inevitable and that coastal defense required fast attack craft, initiated the Motor Torpedo Boat program. The concept was simple. Small, fast boats armed with torpedoes could attack larger warships in coastal waters where destroyers and cruisers couldn't operate effectively. The British had developed motor torpedo boats achieving speeds exceeding 40 knots. The Italian Navy operated MAS boats that had sunk an Austro-Hungarian battleship in 1918. The technology was proven. The Navy needed American versions. 3 manufacturers submitted prototypes: Electric Boat Company, Elko, Higgins Industries, and Huckins Yacht Corporation. All 3 designs used plywood construction for lightweight, multiple engines for redundancy and speed, and torpedo tubes for armament. But all 3 encountered the same problem: the Navy's fuel regulations. Bureau of Ships specifications mandated that small craft use 80-octane gasoline, the same fuel used in automobiles and trucks. The regulation existed for sound safety reasons. Higher-octane aviation fuel was more volatile, more prone to explosion if exposed to sparks or flame, and more dangerous in confined spaces of small boats. Aviation fuel required extensive safety precautions, vapor recovery systems, flame arresters, and specialized handling procedures that weren't practical in combat vessels expected to operate under hostile fire. But 80-octane fuel imposed severe performance limitations. The Packard V12 marine engines powering PT boats were designed for higher compression ratios optimized for 100-octane fuel. Running them on 80-octane required reducing compression, limiting RPM, and accepting power outputs well below the engine's potential. The result was boats that achieved 38 to 41 knots maximum speed, fast by destroyer standards, but inadequate when chasing Japanese landing craft or fleeing Japanese destroyers that could match or exceed those speeds. The first PT boats deployed to the Philippines in 1941 demonstrated the problem immediately. During the Japanese invasion following Pearl Harbor, PT boats attempted to intercept landing forces and attack Japanese warships. The boats were too slow to catch troop transports, too slow to escape when Japanese destroyers responded, and too slow to reliably position for torpedo attacks. PT boat losses were catastrophic. Nearly the entire Philippine PT boat force was destroyed or abandoned during the retreat to Australia. After-action reports from surviving crews were unanimous. The boats needed more speed. Navy engineers understood the solution: allow PT boats to use 100-octane aviation fuel, increase engine compression ratios, and accept the performance gains. But the Bureau of Ships Fuel Safety Regulations explicitly forbade this. The risk of catastrophic fire or explosion was deemed unacceptable. PT boats would continue using 80-octane fuel and accepting the performance limitations that resulted. Which brings the story to a civilian mechanic at the Elco Naval Division who decided that the regulations killing PT boat crews needed to be ignored. His name was James Dewan, not the actor, but a marine engine specialist with 2 decades of experience building racing boats. Dewan had worked for Elco since 1938, initially in civilian yacht production, then transitioning to military PT boat construction after Pearl Harbor. His expertise was engine optimization, extracting maximum power through carburetor tuning, ignition timing, and fuel mixture adjustments. Dewan understood that the Packard engines in PT boats were operating far below their potential because of the fuel restriction. In May 1942, Dewan approached Elco's production manager with a proposal: modify one PT boat to run on 100-octane aviation fuel, increase compression ratios, install enlarged carburetors, and test the performance gains. The production manager refused. Navy regulations prohibited the modification. The Bureau of Ships would never approve it. Elco couldn't risk losing military contracts by violating specifications. Dewan proceeded anyway. PT-59, a newly completed boat awaiting delivery to the Navy, sat docked at the Elco facility undergoing final systems testing. Over 3 weeks in June 1942, Dewan and 2 assistant mechanics worked night shifts, systematically modifying the boat's fuel and engine systems. The modifications were extensive. Engine compression ratios were increased from 6.4 to 1, optimized for 80-octane fuel, to 7.3 to 1, suitable for 100-octane. Carburetors were replaced with larger units providing increased fuel flow. Ignition timing was advanced to match the faster combustion of higher-octane fuel. Fuel lines were upgraded to handle the increased flow rates. Most critically, the fuel system was modified to accept aviation gasoline, requiring new filters, venting systems, and safety interlocks that weren't part of standard PT boat specifications. The work was conducted without authorization, without documentation, and in direct violation of Navy technical orders. If discovered before testing proved the concept, Dewan faced termination and potential criminal prosecution for tampering with military equipment. Elco faced contract cancellation. The boat itself would be condemned as unsafe and scrapped. But Dewan understood something Navy engineers didn't. PT boats already carried torpedoes filled with high explosive. The safety argument against aviation fuel, that it created unacceptable explosion risk, ignored the fact that every PT boat carried weapons more dangerous than any fuel tank. A torpedo warhead contained 466 pounds of Torpex explosive, equivalent to approximately 600 pounds of TNT. If a PT boat took enemy fire sufficient to ignite fuel tanks, that same fire would almost certainly detonate torpedoes, destroying the boat regardless of fuel type. The supposed safety benefit of 80-octane fuel was illusory. Moreover, Dewan's racing experience taught him that fuel volatility could be managed through proper system design. Aviation fuel was dangerous in poorly ventilated spaces with inadequate vapor control. But with proper venting, flame arresters on carburetors, and automatic shutoff systems that isolated fuel tanks if fire was detected, the explosion risk was manageable. The Navy's blanket prohibition reflected institutional conservatism rather than engineering necessity. In late June 1942, Dewan completed the modifications. PT-59 sat at the Elko dock, externally identical to every other PT boat, but internally transformed. The fuel tanks had been drained of 80-octane gasoline and refilled with 100-octane aviation fuel, obtained from a nearby Army Air Forces depot through channels that were never clearly documented. The engines had been test-started briefly, confirming they ran smoothly on the new fuel. What remained were sea trials to measure actual performance. The test run happened at night, without Navy observers, on July 28, 1942. Dewan and a volunteer crew, 3 mechanics who understood they were participating in an unauthorized test, took PT-59 into Newark Bay after dark. The route was carefully planned, out through Kill Van Kull into lower New York Bay, then south toward Sandy Hook, where open water permitted high-speed runs away from commercial shipping. At 22:15 hours, in calm seas with minimal wind, Dewan advanced the throttles to maximum power. The Packard engines, now running at compression ratios they were designed for and burning fuel they were designed to burn, produced power outputs far exceeding anything achieved by standard PT boats. The boat accelerated violently, bow rising as the hull climbed onto plane, then leveling as speed increased. The tachometers exceeded redline, 2,400 RPM, well above the 2,200 RPM that Navy technical orders specified as maximum. But the engines ran smoothly, temperatures remained within acceptable limits, and the sound was different, a deep roar replacing the labored whine that characterized 80-octane operation. Dewan glanced at the knot meter, a mechanical speed sensor trailing behind the boat. 44 knots, 46, 48. The boat was still accelerating. At 52 knots, roughly 60 miles per hour, Dewan reduced throttle, bringing the engines back to cruising power. PT-59 had just exceeded the speed of every other PT boat in existence by 10 knots. The performance gain wasn't marginal, it was transformative. A boat that fast could catch anything. It could escape anything. It changed the tactical equation completely. But proving the modification worked was easier than convincing the Navy to approve it. Dewan reported the results to Elko management the following morning. The production manager, terrified of the Navy's reaction, ordered the boat returned to standard configuration immediately. The aviation fuel was to be drained, the engine modifications reversed, and all evidence of the unauthorized test eliminated. Elko couldn't afford to be associated with a project that violated Navy regulations, regardless of performance gains. But Dewan had documentation, timing data from the test run, fuel consumption measurements, and engine temperature logs proving the modifications worked safely. He sent copies to motor torpedo boat squadron commanders in the Pacific, betting that combat officers would value performance over regulatory compliance. One of those copies reached Lieutenant Commander John Harley, then serving as operations officer for Motor Torpedo Boat Squadron 3 in the Solomon Islands. Harley, who had experienced firsthand the inadequate speed of standard PT boats during operations against Japanese destroyers, recognized immediately what Dewan's modifications meant. A PT boat achieving 52 knots could execute tactics that were impossible at 41 knots, overtaking fleeing transports, evading pursuing destroyers, and positioning for torpedo attacks against faster enemy vessels. Harley forwarded Doohan's data to Admiral William Halsey, commander of South Pacific Forces, with a recommendation: authorize field testing of the aviation fuel modification on PT boats operating in combat zones. If the modification proved effective and safe in actual operations, regulations could be revised. If it failed, only a few boats would be affected. Halsey, facing desperate tactical situations where PT boats represented the only available naval force in many areas, approved the test. In September 1942, 4 PT boats in the Solomons were modified to use aviation fuel, with Doohan specifications transmitted via encrypted teletype. The modifications were conducted by squadron mechanics using parts scavenged from damaged aircraft. The results exceeded expectations. PT boats running on aviation fuel demonstrated dramatic performance improvements in every category. Maximum speed increased from 41 knots to 52 knots. Acceleration improved. Time to reach maximum speed decreased by 40%. The range increased because the more efficient combustion extracted more power from each gallon of fuel. Most critically, the boat's tactical flexibility expanded enormously. They could engage targets previously too fast to catch, evade enemies they previously couldn't escape, and execute attack profiles that required rapid maneuvering at speeds standard boats couldn't sustain. Combat reports from squadrons using modified boats documented the difference. During operations in Blackett Strait in October 1942, modified PT boats successfully intercepted and sank 2 Japanese destroyers attempting to reinforce Guadalcanal. Standard PT boats had attempted similar intercepts previously and failed because they couldn't achieve favorable attack positions before destroyers detected them. The speed advantage provided by aviation fuel meant modified boats could position for torpedo attacks before being detected, or could close the distance rapidly after initial detection. Japanese forces noticed the change. Intelligence reports captured after the war revealed that Japanese naval officers noted American PT boats had suddenly become faster, appearing in unexpected locations and achieving tactical results that previous PT boat operations hadn't accomplished. Japanese destroyer captains, accustomed to outrunning American PT boats, discovered they couldn't escape anymore. But the modification's success created a bureaucratic crisis. Bureau of Ships regulations still prohibited aviation fuel in small craft. The field modifications authorized by Halsey were technically illegal, violations of Navy technical orders that should have resulted in disciplinary action. Yet combat results proved the modifications saved lives and achieved tactical objectives impossible with standard boats. The Navy faced an uncomfortable choice: admit regulations were wrong and revise them, or court-martial the officers and mechanics who had ignored regulations and won battles. The Navy chose pragmatism. In January 1943, the Bureau of Ships issued revised technical orders authorizing use of 100-octane aviation fuel in PT boats, equipped with specified safety modifications, improved venting, flame arresters, automatic fuel shutoff systems, and fire suppression equipment. The new specifications essentially codified Doohan's modifications while adding bureaucratic oversight and quality control. Production PT boats built after March 1943 incorporated the modifications from the beginning, using high-compression engines designed for aviation fuel. Existing boats were retrofitted during regular maintenance periods. By mid-1943, virtually the entire PT boat fleet operated on aviation fuel, achieving performance that earlier boats couldn't match. The impact on the Pacific War was significant, but difficult to quantify precisely. PT boats equipped with high-speed modifications achieved higher kill ratios against Japanese vessels, suffered lower loss rates during engagements, and enabled tactics that standard boats couldn't execute. Specific battles, such as the destruction of Japanese supply barges in the Solomons and the interdiction of evacuation attempts at Guadalcanal, depended on the speed advantage aviation fuel provided. But the modification's greater significance was doctrinal. The aviation fuel modification demonstrated that combat effectiveness sometimes required ignoring safety regulations designed for peacetime operations. Navy regulations existed for valid reasons, preventing accidents, maintaining standardization, and ensuring quality control. But regulations designed to minimize peacetime risk could impose unacceptable operational constraints during wartime. Finding the balance, accepting necessary risks while avoiding reckless ones, required judgment that regulations couldn't codify. James Doohan's decision to modify PT-59 without authorization represented exactly this judgment. He recognized that the fuel regulation was killing PT boat crews by limiting performance in combat situations where speed meant survival. The risk of fuel explosions, while real, was smaller than the risk of being overtaken by Japanese destroyers or failing to intercept enemy transports because of inadequate speed. Doohan's unauthorized modification violated regulations but saved lives. The Navy's eventual acceptance of the modification validated Doohan's judgment, but highlighted institutional resistance to innovation. The performance benefits of aviation fuel were obvious to anyone who understood marine engines, yet Navy bureaucracy required combat proof before revising regulations, accepting unnecessary casualties during the time required to gather that proof. A system that couldn't recognize obvious improvements without formal testing was a system that needed reform. Post-war analysis confirmed the modification's impact. PT boats using aviation fuel achieved average speeds 25% higher than standard boats, reduced enemy contact to engagement time by 35%, and increased successful torpedo attack rates by approximately 40%. These improvements, while significant in individual engagements, accumulated across hundreds of operations into strategic effects. Japanese supply lines in the Solomons and New Guinea were interdicted more effectively because PT boats could catch vessels that would have escaped slower boats. Japanese evacuation operations suffered higher losses because PT boats could pursue and attack retreating forces. The modification's cost was minimal. Fuel explosion incidents increased slightly. PT boats using aviation fuel experienced marginally higher fire rates when hit by enemy fire, but the increased fire risk was offset by decreased hit rates. Faster boats were harder to target, evaded more attacks, and presented more difficult firing solutions to enemy gunners. The net effect was that modified boats had lower total loss rates than standard boats, despite slightly higher fire risk per hit. James Doohan received no official recognition for the modification that transformed PT boat effectiveness. Navy records credited combat experience and operational requirements for the transition to aviation fuel, erasing the unauthorized development that actually produced the change. Doohan continued working at Elco through the war, supervising PT boat production and training mechanics in the proper implementation of the modifications he had pioneered. The final irony was that the outlawed modification became mandatory. By 1944, operating PT boats on 80-octane fuel was prohibited, the exact opposite of 1942 regulations. The modification that would have resulted in court-martials 2 years earlier became standard practice, required by the same Bureau of Ships that had initially forbidden it. The bureaucratic reversal was complete. Modern naval special operations craft, The descendants of World War II PT boats prioritize speed above almost all other characteristics. Special operations craft Riverine, used by Navy SEALs, achieve speeds exceeding 45 knots using advanced hull designs and modern engines. Mark V special operations craft exceed 50 knots. Both are designed from the beginning to maximize speed, incorporating lessons learned from PT boat operations that proved speed was the most critical survival characteristic for small combat craft. The doctrinal lesson persists. In special operations, speed enables tactics that firepower and armor cannot. A boat fast enough to choose when and where to engage can defeat larger, more heavily armed opponents by attacking from unexpected directions, evading counterattacks, and withdrawing before enemy forces can respond effectively. PT boats demonstrated this principle. Modern special operations craft embody it. In naval museums today, PT boats sit preserved as artifacts of a specific tactical era. Museum placards describe their plywood construction, torpedo armament, and operational history. Technical specifications list engines, speed, and range. No mention that the speed specifications changed mid-war because a mechanic violated regulations and proved that the rules designed to keep boats safe were actually getting crews killed. What the placards don't explain is that military effectiveness sometimes emerges from unauthorized innovation. The PT boat that changed naval tactics in the Pacific was modified illegally, tested without permission, and deployed in violation of Navy technical orders. The modification succeeded not because it followed proper procedures, but because it ignored procedures that were wrong. James Dewan's outlawed fuel modification created America's fastest patrol boats and established tactics that defined naval special operations for the next 80 years. The mechanic who risked his career to prove that speed mattered more than regulations established principles that guide naval special operations to this day. Sometimes the outlawed idea is the correct idea. Sometimes breaking the rules is the only way to survive. The thunder of 3 Packard engines running at 2,400 RPM on 100-octane fuel proved faster than regulations could follow.